Good afternoon to you all. I'm Kapil Oberai. Welcome to the session on recent trends in geoinformatics. I'm from the geoinformatics department at IARS. So in this lecture, we'll try to see the various trends in the area of geoinformatics. As you can see on the slide here, we'll try to cover the things mentioned one by one. But before that, we'll try to review what we mean by geoinformatics and how the whole GIS evolution has happened and the role that IT and ICT has played. So geoinformatics, as we understand, is a suite of technologies primarily including the GIS, Earth observation or remote sensing, GNSS for positioning devices, along with the ICT. Now, geospatial technology has influenced uh, various aspects of our life, and if you see in our day-to-day lives, we are using geospatial technologies, whether it could be through when we watch television or when we are booking or receiving some product from e-commerce, are all powered through these geospatial technologies. And if we look at the progress of GIS, which started way back in 1960s with the Canadian Geographical Information System, we have come a long way. As you can see from this infographic that I'm showing here along with the timeline, so the Canadian Geographical Information System was basically a mainframe based system way back in 1960s, followed by the development of the desktop based systems, or we call it personal computers, thereby leading to a standalone GIS, which means the GIS on individual machines. Followed by somewhere around 1990s, we also have the distributed GIS, including either internet and mobile based GIS, followed by the coming of the technologies like cloud computing. So we have a cloud based GIS systems, and then due to the need for high end processing, maybe high-end spatial data analysis or processing, there was a need felt for having a cyber infrastructure or high-performance computing, thereby leading to a term of cyber GIS. And nowadays, in the artificial intelligence era, more with the coming of the generative AI, we also have the concept of an autonomous GIS. Now, GIS, as I mentioned, has touched many industries and even our common day-to-day lives, and we have seen some good examples in our healthcare sector during the COVID-19 also. Now, GIS has also made use of the technologies upliftment, just like use of the cloud computing, IoTs, artificial intelligence, machine learning, and hence, as you can see from this infographic, the evolution of GIS, because of the availability of these technologies, the GIS has also evolved from a big mainframe based systems to a GIS system on individual machines, to GIS being available over the net through through the web browser, or GIS on the go through a mobile based interface, through or leading to the availability of cloud computing, leading to the cloud GIS and so on. Now, talking about the first trend is obviously we are in the era of the artificial intelligence, and it has touched it is being used in various sectors, including in the geospatial. So we use the term geospatial artificial intelligence just to highlight that we want to use this technology for in the geospatial area, and can be defined as the application of AI and ML for the geospatial data, and can be used for analyzing, interpreting, and also making predictions. Aim is to find the geographical patterns and understand the underlying spatial phenomena. So here we are trying to combine the GIS with the AI, so as in a fast manner we should be able to, and also in automatic way, try to understand the pattern and analyze the spatial data. And you can see various kinds of applications in the literature that could be either object detections, which could be identifying the trees, the individual vehicles. It could also be classification problems like land cover classifications, also the digitization process, and also the change detections based studies that could be either identifying the land cover changes or new buildings that have come up. Now, the reason that we are using this geospatial artificial intelligence is because it can save us, compared to a manual effort, a lot of time, because it can automate the repetitive task. It could be classification problem or a clustering problem or a regression problem, and then we could get the result in a fast manner once a model is being trained. And also, since once the model is being trained based on the data sets, we could eliminate the human error that is involved in a typical workflow. The whole aim of having a Geo AI based algorithm is that the system or the algorithm will be able to analyze the geographical data and learn the pattern automatically instead of individually programming that particular systems to understand that underlying pattern or get the inference from the data sets. Now, this infographic on the right is showing one example of predicting the groundwater level. So the objective here is for the using remote sensing and GIS and trying to establish the linkage of groundwater level with the geological and meteorological factors and to predict the groundwater level. So the process generally in the geospatial artificial intelligence primarily starts from the machine learning perspective is the data collection followed by pre-processing and data cleaning, and then we divide the data sets into two parts. One is the training data sets that we feed to the algorithm, and then we keep the testing data for later for checking how does the model has performed, and generally we split them into 70-30 kind of a ratio. So training data primarily consists of knowing the features, maybe it could be one attribute, could more than one, and also the label in case of, let's say, the classification problem. And the aim is to identify the algorithm, feed the data into the these training data sets into the algorithms. The algorithm will learn based on the data sets and try to, given this testing data, we can check the accuracy. And then similarly, we could also try, once the model is trained, then we can give him the new input data sets and it can predict based on the information it has learned from the underlying training data. And then once the model is trained based using the accuracy metrics, it could be R square or RMSE, we can decide the fitness of use of such kind of model. If we are not happy, then we can repeat the process or include more training data sets to arrive at the desired results. Now, if I just talk about from the higher perspective, how does this AI, ML and DL are related, and then how it caters to our geospatial AI. So first term is the artificial intelligence, which is a superset, is primarily the simulation. In this we are trying to see if we can simulate the human intelligence through machines. When we say machines, we are talking primarily about the computer systems. Now, machine learning is a field of an artificial intelligence, and the aim here is can we feed data to the algorithm so that machine can learn the underlying pattern without being explicitly programmed. Now, to understand this, let's see how we develop kind of any given a problem statement, how we are actually building different softwares to cater to different needs, and how does that process differs from a machine learning process that we are talking about. So this is a induced intelligence life cycle. This is where the business team or the user will give their broad requirement. The coders will try to understand those requirements and try to build the software systems based on the rules that the business teams has defined. So primarily the output in this case is a program, which primarily is being used by the end user, where he can give input to that program and the program will return back the output to the user as per the rules being implemented onto that underlying software. So in the induced intent approach, given a business. Now, if you look at this graphic again, so AI, ML and DL is mostly used by the data scientists, but this generative AI has opened up this field, so now it is accessible to the developers and also to the end users who can use such kind of algorithms and models and can use them for the different use cases. Now, so the So the GPT kind of an model allows the user to interact with the system through a chat-based interface. Hence, if you when I was showing the evolution of GIS, where I was mentioning the autonomous GIS through the generative AI, the same concept is also being used nowadays in GIS also, and you will come across various plugins in GIS systems or softwares that are trying to create that kind of a chat-based or chatbot-based system where the user could interact with the underlying geospatial data sets using either a prompt-based interface or in the chat mode. This is the paper that I'm referring. You can see the reference mentioned at the bottom. So the idea here is, given a prompt, can the system helps in answering the question. So if you see the GIS workflow, primarily it involves various kind of stages which we need to go through in a step-by-step manner. But through this prompt-based interface, it could increase the accessibility of such softwares so that the end user, without much, let's say, training on those on the software, can also be able to use it, because he will be primarily using the natural language for interacting with the system. In this case, it is identifying, let's say, school within 1 kilometer radius from a particular hospital. So the system will try to comprehend what the user is prompting. Based on that, it can identify the suitable data sets and then use the various tools and utilities along with the data sets, and then gives the result back to the user. So this kind of system will enhance what the accessibility and also the usability of these systems. And then also, with the power of this generative AI through a natural language based kind of a interface, more and more users will be able to use without much learning curve from the geospatial perspective. Now this the same Geo AI from the generative AI perspective has also been evolved from a simple, let's say, prompt based chat interface to the underlying GIS system, to think in terms of a lighter like a co-pilot. So the term, I think, co-pilot, you must have been recently hearing. So mostly from a generative AI perspective, like from the Microsoft Copilot, which allows to integrate these AI large models inside the Microsoft based environment. So the co-pilot, the term comes from an airline where we have a main pilot and his colleague who used to support him into the operations of an airline. Similarly, we can think about GIS co-pilot as our personal assistant or our personal colleague who can assist us in various tasks, in this case answering our geospatial related queries. And then the workflow will typically look something like this. So the human users will interact with a chatbot or a GIS co-pilot, and the co-pilot will have various modules that could be fetching data, query module. It could help in either generating the code or reviewing the code or debugging the code. Based on the user query, the co-pilot will be able to retrieve the necessary tools. Those tools could be either vector, raster, or a combination of those tools. And in this case, they can also inherently call the built-in GIS tools inside the particular GIS software, let's say QGIS. So they will be able to call the underlying, let's say, processing tools like buffer, slope, select by attribute, and similarly for the raster and vector tools. Now the pilot will also be able to extend the capabilities by calling the external or customized tools that may not be available in the underlying GIS software. So think in terms of, we have a GIS software, we're trying to build an interface through linking this models, generative AI models with the QGIS, so they can call the underlying functionalities either by generating the code per se or calling those functionality through the prompts. And then they can also access and link the external or the customized tools, which could be some vector-based tools like GeoPandas library, or plotting, maybe Matplotlib, and so on and so forth. So this paper that I'm referring, that I mentioned the reference below, this has provided a plugin, so that is also available for the QGIS environment. So if you can visit that paper, you will get an access to the link, or you can go to the QGIS plugin section and search for autonomous GIS. you'll be able to download this plugin, which provide a spatial analysis agent, which is having these four windows. One, and on the below is where you mention your data path. So suppose you want to prompt something based on to this generative AI system based on this plugin, so you can provide your input data set. So that primarily ground the system to know that what all data sets he need to crawl to have an information about the data sets, followed by second window where he can put out his request in a prompt, and the information panel and the code display, which will be once the system understand the prompt what the user trying to communicate, it will try to convert the request into the equivalent GIS based workflow steps, try to execute one by one, and the code display will, in this case they are trying to convert the request from the steps to the equivalent PyQGIS code, or could be calling the natively the QGIS processing algorithms based on the user request, and the output is added dynamically onto the map interface. In this case, it is the QGIS. So such kinds of platforms are nowadays being available. So this is the example of QGIS. Now, for example, if the request is, can you please create 2,000 feet zone around each healthcare facilities to identify areas of service coverage. So based on the data sets that are given and based on the query, it can come up with the typical step, which is identifying the tool, let's say buffer, executing the geospatial workflow, which is the buffer, and then finally the output is loaded back to the map canvas. So as you can see here, what it's doing is trying to convert the prompt into identifying the probable tools, and then calling the equivalent QGIS processing algorithms using the processing APIs by calling the buffer, which in turn creates a new layer which is added to the map canvas. So from the geospatial AI is one of the trend that you will see quite predominantly now and being used for various scenarios. Moving to the next is the concept of Internet of Things, and they are also revolutionize the way in now we are accessing and trying to consume the real-time data sets in our GIS models. So IoT, or the Internet of Things, primarily refers to a system of interconnected devices, and as the name suggests, they are communicating through the internet, and then gathering data from the surrounding via the onboard sensors on that device, and then transmitting that data being collected through the internet without any human contact. So that the IoT devices could be of various kinds. That could be like a smart transport, it could be a bus that we want to track, it could also be smart health kind of devices, or let's say the smart watch which we can wear, which can gives us information about the heartbeat and other kind of parameter details. And similarly, there could be other kinds of information from the ground that we want to collect. It could be temperature, pressure, or air pollution kind of sensors that we want to collect data from. Now, the application of IoT in GIS has opened new possibilities, which allows us to analyze and visualize the data in near real time. For example, this figure demonstrate the, let's say, the CCTV cameras that are available to a particular city, and then clicking on a particular location. So these balloons are showing the location of the CCTV camera. So clicking on them, one can see what is the situation on the ground, and similarly we can also see how many the information on the ground based on this real-time information that we have captured. Now this kind of technology is only possible with the evolution of the, let's say, the kind of telecommunication technology that has evolved from the way back from 1G to analog phone to now 4G and 5G, where we are talking about connected devices having a large bandwidth, high speed internet access. Through that only has led to creation of such kind of, let's say, technology through which we could collect data using the IoT devices onto the field and then also collect and manage those devices. So if you see the benefits, it has increased the, maybe from the proactive maintenance could be done. There is a minimum of user interactions and more enhanced services, more location awareness can be done through using such kind of IoT based sensors and linking them to the GIS. Now there are various, in the literature you will come across various use cases of how the IoT devices are being used in the GIS environment. And as you can see on the left hand side, there are various applications from urban, transport, disaster and so on. For this lecture, let's just focus on three of these things that I've highlighted here. For the disaster management, the IoT could provide us information related to the real-time information onto the ground. Thereby, the integration of IoT and GIS could lead to enhancement of the management process. Similarly, from the environment monitoring perspective, they can support us in the data collection and real-time monitoring, hence enhancing the management and the decision-making capabilities of the decision makers. Similarly, in the case of the healthcare, they could help, suppose in this case, maybe monitoring the physiological status of the patients remotely, which is very beneficial from the both from the patient perspective and also from the healthcare provider perspective, because as and when the situation is happening and the patient's necessary parameters could be monitored and interventions could be taken, and similarly the monitoring system could be enhanced to support that patients in a much better way. So we'll come across various such utilities either from smart farming or precision farming to all the way to healthcare, urban, disaster and so on. The next trend that I wish to discuss now is the concept of the big data, especially from the geospatial perspective. So we talk the term spatial big data, which primarily refers to data sets that are of large collections and of diverse types, which is somehow difficult to store and manage through the standard state-of-the-art approaches. When we say state-of-the-art approaches, in this case we are talking about using a typical database system based on the relation systems. Now, the one way to characterize the spatial big data is through the V's. We talk about volume, velocity, variety, veracity, and the value. When we talk of the term volume, we are talking about the amount of data that is being generated from diverse sources. So this just talks about the sheer size perspective. The velocity talks about the speed at which the data is being generated and needs to be processed. Now the variety talks about the different data types. It could be the structured data or the example of structured data could be one that we could it can be Excel file or let's say a comma separated values, or from the pure database perspective it could be a relation database schema. And then we have a completely opposite of that called as unstructured. So this is something we can get from, let's say, either a social media post or a message post, wherein the content that the user can want to communicate will not follow any structure. It could be images, could be text, it could be English, it could be Hindi, emojis, and all could be mixed match. Then we also have a somewhat kind of semi-structured, which is in between the structured and the unstructured. A good example is of like a XML or a JSON based documents, which allows us to have some fixed format and some arbitrary. The next V is talking about is veracity, which talks about authenticity or trustworthiness of the data sets, which is very, very important when we want to analyze, let's say, especially the data sets where the authenticity can be a question mark. For example, the data sets from social media platforms, especially related to attribute based accuracy or the location based accuracy. Then the whole aim of using this big data and coming up with the analytics is being given by the fifth we call as a value, which is the business value that could be extracted or the insight that could be extracted from such data sets that could be used for informed decision making. Now when we talked about the various data sources of the spatial big data, so few are pretty much obvious, like remote sensing or satellite based images, and obviously they are also increasing over a period of time. And there are not only let's say so there are various spacefaring nations that all have the satellite provide earth observation based satellite images. From for example, for ISRO, we have around 55 satellites, around of which 21 are earth observations. Similarly, there are other programs from various other countries, all contributing to this gamut of data that is being collected. The other sources of data are the surveying and mapping data that is collected through traditional mechanisms. The new kind of data sets that we are looking is the social network data sets, because these social media data sets like Twitter, Facebook, and so on allows user to post their views and opinion. It could be about products, services, usage of those services. So people want to cater to that, use those kinds of posts that the user is posting and use them to analyze their opinion, views about a particular product or services. The other diverse kind of data sets, if you see, is the IoT, which is sending a very fast velocity kind of information from the underlying sensors being connected to the internet beam at every 1 minute or 2 minute interval. Then we also have a mobility kind of data called as a location based data, to find primarily used for optimizing the mobility, the work, the flow of it could be the vehicles and other movements. Now, if you talk about the pure size of the data that we are increasing, the one estimate says that around 2025 we'll have around 175 zettabytes of data. So that vast amount of data will leads to newer management strategies. So the traditional way of using a relational system will not be able to solve the problems, because the relation system are primarily made for handling only structured data. But considering the different types of data like structured, semi-structured, unstructured, so new tools have come up. Those can fall under the category of either Hadoop based solutions or also the Spark based solutions. And then we also have a NoSQL database which allows us to store data sets either in a column, graph, key value, or a document based format. MongoDB is a good example of storing the this kinds of data sets, semi-structured kind of data sets, document oriented with the geospatial capabilities. So so for storing such vast data, there are different kinds of tools has to be used in order to make sense and inherit or extract the insight from the underlying data sets. Now the from the evolution of GIS again, so we from the mainframe to the desktop to the web. Now web also allows the user to more number of users to access the geospatial data and services. So compare this to a desktop based GIS software where one person can only use that particular software at one moment of time, compared to GIS being accessed over the net, wherein lot n number of users should be able to access the data. What they required is the connection to the internet and a web browser. Now this internet or web-based GIS works on the model of client and server architecture. Now we can think of dividing the task either among the client or a server. Now client is a requester for information and server is a provider for information. So in a typical request response model, the client will use the web browser to make a request to the server, because the data and the application is residing on the server side, which is fetched through the URL over the net, and then the response is being generated back to the user. So we can think in this term of a request and response cycle. It is like, suppose you want to visit Bhuvan or Google Maps. So we open the browser, type the domain name. The request is translated to the web server, which in turn pass the request to the map server, which process the GIS data, create the maps, and the output is again sent back to the browser for him to view. A good thing about such kind of web-based or internet-enabled GIS is, one is that more number of users will be able to access it. The user will be able to get access to the real-time data. Dynamic data could also be added and updated. We could interlink multiple data sets together, And other advantage will be that it will be primarily be a cross-platform application, because what the user required will be the web browser to access with the internet accessibility. So whether that web browser runs on a Linux or a Mac machine will not make that particular difference. This is unlike your desktop based environment, where let's say if you are working on Windows, then you need to install QGIS for Windows versus let's say QGIS on Linux or QGIS on Mac system. So this web-enabled system try to combine the power of internet, the dissemination platform, along with the capability of GIS that we could access over the net. And then the various elements in a web-based GIS applications are, as you can see from this graphic, is what we need to have is a web page or a web application through which the user will be interacting with the data sets and the algorithm or the services. Now, when we open any web-based GIS applications, the traditional tools or things that you could find out is the base maps, which are the underlining providing a geographical context. It could be Bhuvan maps, Google maps, or Bing maps like kind of thing. And on the top we add our own operation layers called as a thematic layers, and then we provide various kind of tasks and tools that could be simple GIS tools like panning, zooming, back and forth, identify, and then those are powered through the data that is stored onto the geodatabase onto the server side. Now we are also moving ahead from web as a WebGIS application from pure, let's say, visualization platform, wherein all the, let's say, the GIS layers are being put across to the user for him to view, which he can put it on and off and then can arrive at his own kind of a judgment based on that data sets, to a more kind of a dashboard based environment, which provides the key information about the underlying phenomena that we want to study all on a single page. And we have seen these dashboard during the COVID times, the most popular being this John Hopkinson University COVID dashboard, which was very used, and you could have heard about it in the newspaper and also in the television. So if you look at these kind of dashboard, it provides the basic key performance indicators. In this case is the number of how the COVID situation is moving, progressing, along with indication of, let's say, the person infected country wise. We can zoom to that particular country and see those native details, sorry, so those details specific to that countries. And such dashboard concept was subsequently used both at the country level and also at the various state government also started using during the COVID times to see the ground situations. So basically they provide us a good information for the decision makers to at single window to have a idea about the situation onto the ground so that he could make some informed decisions. In this case, it is suppose we want to identify the area, also see the population, the employment rate. So the moment we zoom to the particular district or a region, all these graphs will change. So basically allows us to aggregate the data and we can view the different parameters in a much more meaningful way instead of just maybe browsing the data through a simple web-based interface. Now we are also moving from the, let's say, visualization to a, let's say, a dashboard system which allow decision makers to make much more sense of the data sets that being provided, to kind of an online processing where the user will be able to process the data online without knowing about the let's say the underlying GIS software per se. One of the example that I'm showing is example of online spatial clustering. Now in our GIS domain, we also have a standard called as the web processing service from the OGC, which primarily streamline the process of exposing algorithms. In this case, it is clustering algorithm as a web processing service over the web, which the client can access using the any compliant client. That could be desktop or that could also be the web-based thing. Again, because it is OGC standards, the interfaces are primarily standardized. That is like get capabilities, which is like an endpoint, will give you information about the algorithms that particular server is being serving. To know more about a particular algorithm, we can use the describe process uh, uh, interface, which will talk about a particular algorithm will take how many parameters. And once we understood that, we could call the third method, which is the execute, wherein we can call the underlining algorithm on from the server side, passing the desired data sets, and we get the output. So here the user don't need to have a dedicated GIS software on his machine. He can work through a simple web-based interface also. So considering this clustering algorithm, here the user can just directly upload, let's say, the location data containing the longitude and latitude and other attributes which are passed over the net and submitted to the remote server where the DBs, let's say in this case a density-based scan clustering algorithm was implemented, which execute that request, and the output is given in the form of a KML file which you can visualize and see. So considering this, that he don't need to have a dedicated GIS software wherein he could execute it, but on the fly those kinds of processes could be done, and thereby increasing what the end users, so that they could also be able to use and make sense of these data without maybe knowing how to operate that particular GIS software. Now, so moving from, let's say, again web, we are moving from the visualization to the dashboard to kind of online geo processing. Nowadays people are also looking at coming up with the decision support kind of a system wherein the user could be given a kind of tool wherein they can come see different scenarios and then arrive at a particular solution based on the by comparing various scenarios. So this is showing one example of a decision support system for, let's say, the suitability thing. Here the layers that are being considered are distance from drainage, distance from road, distance from settlement, and distance from vegetation. So this is a like a site suitability study for habitat. Here the user is given an option. So based on the given 4 layers, the user can define his own weights or can give ranking to the various criteria. Let's say distance from drainage 0 to 1000 he is giving highly suitable, 1000 to 2000 suitable, and so on. And then so based on his scenario building, he can give different rankings to each of those 4 layers. So this is about the first layer, and similarly for the, let's say, the vegetation layer, where he can decide which vegetation are suitable or not suitable. And finally he can come up with the final suitability map, which could show based on the scenario that he has built and the ranking that is given, the which area are falling under the highly suitable to the low suitable. So now you can think that doing such kind of a providing this decision support system will be useful for the end users, because unlike a desktop based environment where you need to use different tools and able to make sense of that, this kind of systems allow the user to try different scenarios in an online mode, and then he can use accesses through the web based application and make it try different scenarios. The output could be converted to, let's say, a PDF file which he could integrate into some reports or presentations to communicate the understanding for a later discussion use. So nowadays we are seeing a lot of evolution from pure mapping based to a dashboard to processing to also complete decision support systems. Now from the desktop environment to the web environment, now let's come to the mobile based. Now one thing is for sure that there are more mobile users compared to desktop users. So hence there is more appification happening, which the word comes from that more and more user wants, instead of having a, let's say, web-based applications, to have an app kind of interface, because more and more people are having a smartphone, and they want, and then there are more smartphone users, as I said, than from a desktop users. So the idea is to have a mobile first kind of environment where the most of the solution provider are trying to have not only the web-based applications but also the mobile apps. For example, in QGIS we have an option of Q field, which you can use from a field data collection. What I'm also showing on the screen is the example of Arogya Setu that we have seen during the COVID times, which apart from other geospatial functionalities of looking the nearest vaccination site or the nearest COVID center. Also, in the initial days, also allows us to find out are there nearby patients within a particular radius. So for field-based operations, these kinds of mobile-based applications are useful. Now again, the challenge here is because there are diverse kinds of mobile platforms like Android or uh, iOS. Now how to cater to those requirements? So one approach is that we create a let's say a responsive web-based application that could run on different browsers, but to use it you need to open the browser and then type the URL and then access them. The other approach is to have a native mobile app, again for different platforms like for iOS or Android. But again, to have that native kind of a application, you need to make sure that there are two versions, let's say, of the same applications, one for the Android and let's say one for the Windows or the iOS. And any update will also lead to maintaining these two code bases, which also means you should have a dedicated team who should know about working on Android as well as on the iOS. So there are other approaches also. There is also called as a hybrid app, wherein it allows you to create your mobile applications using web technologies like HTML, JavaScript, and CSS, and use some kind of a hybrid app platform like Cordova and other platforms, Ionic, which converts those to the native platforms. Nowadays, there is also the concept of progressive web app, which uh, again try to serve this hybrid based kind of an approach where we try to develop our mobile application using again web technology of HTML, CSS, and JavaScript. However, this do provide some native capabilities like install feature and some kind of a look and feel more of a mobile. It has install capabilities. It works, it just appears like an icon as an app on your mobile compared to the web app where you need to open the app and do it. And other good thing about progressive web app is it also supports or have the built-in capabilities of catering to a offline kind of a mobile app, which could also be useful in some of the scenarios, especially if the internet is intermittent or the connectivity is not that 100%. So then we could also develop using this progressive web app a kind of mobile app that also supports both online and offline capabilities. One of the variant of mobile-based applications is the location-based services, which is one of the widely used geospatial applications. And these are the applications that people are using on a daily basis. So every time you book a taxi or a cab or through Ola and Uber, you are making use of these location-based services. So so apart from providing, let's say, context-aware services based on the location, the advancement here now involves the concept of augmented reality and virtual reality. So the term augmented reality primarily means that we want to combine the real-world environment with the computer-generated superimposition or overlays so as to provide an augmented view of the reality. One way to understand is something like you have a mobile application with the, let's say, augmented AR app installed, and you can point that you can open the app, open the camera, and point it to a particular device, and then so to particular place, and then it could superimpose the information from the remote server and display it on the top of that. So basically we are trying to combine the real world environment where we are physically with along with the digital overlay onto the mobile device. So this could help in inspection, knowing more details about the particular phenomena, and could be seen in the supermarket and other kind of scenarios. Compare this augmented reality to a virtual reality. As the term suggests, virtual, It takes the user to a completely computer generated environment, replacing their physical surrounding with a computer generated based environment. And as you can see here, this involves putting a headgear, and there are various use cases of these VR based applications in the education, tourism, entertainment, and also the healthcares. So these are the, let's say, the trends that you can see from the mobile based systems. Now, from the evolution of GIS, again from the web, mobile to the cloud. Now, cloud provide a good model, because compared to a, let's say, a web-based environment or a desktop environment where you need to have a necessary infrastructure in place to store, manage, and run those GIS applications, cloud computing provides on-demand access to the services. That could be applications, that could be storages, that could be server locations, that could be software applications, that could be accessed over the net. So consider this like a pay per use or a subscription based model, where you want to, say, rent certain capabilities from a cloud provider and want to use them for a particular period of time. One good analogy is like usage of the electricity or water in our homes. We are paid, we are the charge based on the amount of electricity that we are using. Now, cloud computing primarily has three basic models called as infrastructure as a service, platform as a service, and also software as a service. So when we talk about infrastructure as a service, so we are talking about that the here we are interested to use the, let's say, the server or the storages perspective, which we can rent it from the vendor cloud provider. So the vendor will provide us this network storage or processor, and then, so assume like you are, instead of access to a desktop on your in your system lab, you could connect to the net to a virtual machine environment in the cloud provider application, which is kind of a remote based system you can get access to. And over this you can install whatever operating system application that you want to build. So instead of having a physical machine on your premises, you could leverage the those capability from the cloud provider and then build your application on top of it. The second service model is called as the platform as a service. Now in this, as you can see from this figure here, the vendor manages not only the underlying the storage or the underlying hardware, but also the give you pre-configured with the operating system and runtime. And on the top of it, you can put more effort on, let's say, development of the application based on the data sets that you want to configure. So consider this like you want to have a .NET based environment where you want to build certain applications. You can have a platform as a service where you're given that .NET environment, and then you can concentrate more focused on the application building perspective. So you don't need to install the hardware, configure it, install the operating system, configure it, install the necessary libraries, etc., before you can start working on those systems. The third type of service model is called as a software as a service. As the name suggests, it is a pure subscription based model. Consider this like you want to access the software that could be, let's say, a mailing solution like a Gmail over the net, and the complete management of the application running is being done by the solution provider or the cloud provider. The same approach is also being used in our GIS nowadays also, and there are various cloud-based providers who provide GIS capabilities online. One example is ArcGIS Online from ESRI. Then again, from the QGIS perspective, we also have a QGIS, and then there are other commercial players like Kato, Mapbox, and GIS Cloud. Now, the cloud computing has also seen being used in the geospatial arena, and has also led to a whole paradigm shift in the way we try to use or process our data and try to make some generate products out of that. So in a traditional let's say remote sensing based study the steps primarily will be going to the let's say the data provider portal, log in there, download the necessary data sets onto your local machine, do those pre-processing steps, then analyze it on your desktop, and then generate different products. However, with the coming of these cloud-based solutions, one good example is the Google Earth Engine, which primarily provides access to the complete data sets along with algorithms, the computing environment, the scripting environment, all built in. So the user don't need to follow this approach because the data is already ingested, available, ready to use, and the user can put more emphasis on the analysis or making interpretation from the data sets rather than following the basic pre-processing and then analyzing and then generating the data sets. And you will come across various use cases of such platform, and you can use in various domains. It could be forestry application, land cover applications, it could be some disaster management studies. And so if you want to do some long-term studies, when compare this to a traditional way of data download and pre-processing. So if you want to do a, let's say, decadal based study for certain phenomena, so you need to go and download those many scenes, mosaic them, pre-process, corrections, all things that we taught in your first model has to be done before you can process. Compared to the these kind of environment where the data are readily available for you to use them, and you can emphasize more on the inference and the interpretation or the applicability of that, making use of those products for your decision making. So these kind of platforms are very popular. Other is the Microsoft Planetary Earth, and similarly there are other solutions are also available. Now one of the thing that is happening in the cloud-based system is there is also one more model called as a serverless model. Now the whole idea of having a serverless computing is because this kind of a model allows the user to focus more on the, let's say, the application building part and not to manage the necessary infrastructure or management. Now consider this, that suppose you are building some applications and then suddenly suppose there is a load has increased or more number of users have come. Now in that case you have to make sure that your infrastructure should be scale up to support those kinds of large number of users, otherwise the response time will decrease. So in the cloud computing perspective, there is also serverless model where the cloud provider manages the underlying infrastructure along with, let's say, the databases, and automatically takes care of the scaling of both of those code and the database, and we only need to pay for the amount of time that we are using such applications. So the focus here is more on, so let's say given I want to build some functionality, I just focus on the code that I want to build, upload that code using this function as a service module onto that cloud provider. And similarly, if I want to store data, I will use their managed service of a database, store and configure my data there. So the scaling part, depending on the load, will be automatically taken care by the cloud provider, and I only need to pay for the amount of time I'm using this. So consider a scenario as I shown a decision support system where suddenly there is a lot of hike has happened into the traffic. Now in that case, if the resources are not available, the response time or the performance will drop. However, in the case of this serverless computing, the cloud provider will automatically takes care of the scaling. So it will get multiple instances of that particular code, try to create multiple instances, so the user will be diverted to different instances of those applications, and we don't need to manage the infrastructure requirement. So that is another computing model that we could also think about. Now again, there are various providers from AWS, Azure and Google. So the idea here is you just upload your code. So in the AWS, that is called as the Lambda function, and we upload our function either using their code editor or into that function and the lambda based system, create a lambda function, and we just put an event or a trigger. So that trigger could be our own web applications. So the moment somebody, let's say in this case, I'm giving an example of a study that we did using this serverless computing on the healthcare perspective, where we'd want to run the DB scan clustering or other such algorithms. And then the moment we trigger it, the function will be get activated and run. And once the responses come, the system will again come back to the normal stage. So thinking like this, so every time there's an invocation, we are charged based on the amount of time we are using that functionality, and once it is not used, it is there is no charge. So that kind of computing model are also being used nowadays, which also from the cost perspective is very beneficial, and also from the user perspective, because management of this whole process of scaling elasticity is also a cumbersome job, is being handled from the by the cloud provider. Now finally, I want to talk on the open source also, because this is the thing that you will see as a trend continuing, because free and open source software, especially from the geospatial perspective, uh, provide a whole gamut of tools that could be from the desktop environment to the web to the storage like spatial database systems to libraries to server based environments are all available. Now consider any, let's say, domain. When I say, and you can compare it with any proprietary software, you will get a equivalent product in the open source domain. For example, in the desktop, if I talk about, QGIS is a very robust solutions, support a lot of uh, geospatial tasks like vector, raster. There are a whole gamut of extensions or plugins that are available that you could use. So something that may not be natively supported, if you can go to the plugin, you will come across that because of the community linkage, they allows user to contribute to those softwares. So you'll come across a plugin that you can directly integrate and could be used. Now the free and open source software, they offer advantages compared to the proprietary software. First is there is no cost per se, so there is no software cost or the, let's say, the license cost or the renewal cost. So they are free in the terms of usage of those application, and further is the free is more in terms of liberty that we get in the usage of those softwares. So we could access the code, we could modify it, we can put it back and contribute it, we could create a new version and again distribute it, allows customization and other things to be done compared to a proprietary. So we are not, there is no vendor lock-in in the open source. And as I mentioned, from our geospatial perspective, there are a lot of stable and mature products, from both from desktop to web-based to server, even to cataloging, and also the backend spatial database systems. For example, from the backend spatial database systems, we have a Postgres with PostGIS. We also have Spatialite that you could use for data storage perspective. Similarly, sorry. Yeah, so from the GIS server perspective, we also have Geo server, Map server, even QGIS Map server is also there that you can use for hosting of your data sets in the OGC compliant format. From the web processing perspective, what I was showing was PYWPS, but there are other options like 52 knot WPS or degree. Now from the client perspective again, apart from a desktop based, as I mentioned, to build the web applications for the web GIS, we have various libraries. We could use Leaflet, we could use open layers, there is GeoXT, and then other GeoMoose and other kinds of libraries are also available. So for a typical requirement, you will also come across that the open source do provide the suitable solution that you can use. Now, those who want to start their journey in this open source, especially from the geospatial perspective, is I will suggest them to have a look at this OSGeo Live website, which primarily provides kind of a usable. It could be a CD or a thumb drive that you can burn this image into, and come with the all pre-installed all the softwares primarily coming under the OSCO softwares. So from your desktop softwares to your web softwares, all are available, and that is also pretty easy to use, because initially during the early phases it becomes, when you want to evaluate various softwares, it is difficult to try to install various softwares and configure them. And this comes pre-bundled as in the form of either a bootable DVD, or you could have a USB drive that you can burn using that image that you can download, that is around 4 GB to 8 GB, depending on whether it is you are burning on a DVD or the thumb drive. But advantage will be that all the softwares are, as I mentioned in the previous slides, are come built in along with the demo data sets, along with the getting started guides, and obviously that will point it back to the software websites. But that is a good starting point in case you wish to learn these softwares, and also trying to explore various softwares without installing and configuring those things. So with this, I will close here. So in this session, we try to see the some of the trends. We started by learning about geoinformatics and also the evolution of GIS from mainframe Canadian Geographical Information System, started from 1960s, moving on to the desktop, to the distributed GIS from web, mobile, and also to the cloud-based GIS. And now we are also talking autonomous GIS using generative AI, and we have seen trends related to Geo AI, IoTs, spatial big data. The We talked about the web-based applications, their evolution, the trends, and then we have also seen in the final slide the open source and how you could also get started in this. So with this, I will close, and then I will join back again after some time. Thank you. So welcome back. So we got one question from Saswati Sinha. Are there any instances where Hadoop and Spark might be needed to be used together? Yes, it could be, because so Hadoop can be used as an underlying storage, and the Spark can work on the top of that. Because if you have seen that infographic of Spark ecosystem that I was showing uh, today, you'll see that the Spark does not assume any underlying storage infrastructure. So you could run it on the top of a Hadoop, or we can connect to some cloud-based storage, or we could also connect to a NoSQL system also. So yes, they could be used together also. Saraswati, do you have any other follow-up question on this? So I hope that was clear. In case you have any follow-up question, you can post it. I request others also, if they have any doubt or a suggestion or a query that they want to put, can they can put in the chat window. Okay, so there are no further queries. So I thank you all. And then I also want to thank our EduSet team for the support, and then look forward to meeting you next time. Thank you so much.